this video, we're going to carry on with our discussion on magnetic fields. And so far, we've seen that magnetic fields behave slightly differently to electric fields. We know that magnetic fields do no work, and we also know that there cannot be any magnetic monopoles existing anywhere. And this is in stark contrast to electric fields, which of course, neither of which are true. Now we're going to carry on using some of the formulas that we used in the previous video to continue our discussion. And in particular, we're going to use the equation for B right here to go on to derive Ampere's law, which is one of Maxwell's final equations that he formulated. So without further ado, let's get on with it. So in the last video, we had this integral equation for the magnetic field strength B as being equal to mu naught divided by 4 pi times this integral, and this was over a volume of current essentially. So the simplest case of this is a wire where we're actually kind of zoomed into the wire right here, and this wire has a current density, a current per unit surface area of J right here. And this integral was over a volume. So for example, this region of volume right here, where this is obviously a cylindrical volume right here, it would be equal to J, and we had that it was cross-producted with the gradient of minus 1 over R dV. Now this was before we actually evaluated what this del of 1 over R is, which we then went on to show that there were no magnetic monopoles. But at one point we had it kind of looking a little bit like this right here. So if you're unfamiliar with this, yet again, I recommend checking out the previous video. But we can evaluate this del of minus 1 over R as being equal to the derivative with respect to R of minus 1 over R, right there. Now this would actually apply in both cylindrical or spherical coordinates. Wherever you have a radial component, you can just simply take the derivative of this radial component and evaluate it. And since there will only be a radial component, then this is fine to do. You've got a minus 1 over R, so normally you get a minus 1 over R squared, but since there's a minus sign, that will cancel to just give 1 over R squared. So therefore, del of minus 1 over R is going to equal 1 over R squared in the R hat direction, because of course, when you take the gradient of a scalar, you get a vector. So let's go ahead and substitute this in, and we end up with this equation right here. Now, what we're going to do is, whereas before we took the divergence of both sides, we're actually going to take the curl of both sides of this equation now, and we're going to see what we're going to get. So let's take the curl of B right here. So we have curl of B is equal to our constants right here, mu naught divided by 4 pi. And we can bring this curl inside the integral, because as we said before, the integral is over a different coordinate system to our sort of evaluation coordinate system, if you like. So we're going to get the integral of the curl of this whole vector right here. So we're just taking curl of both sides, and we're just bringing it inside the integral right there. Now, whenever you have a double cross product like this, you can actually use what's sometimes referred to as the back cab rule. And basically it's, if you have A cross B cross C right here, you can actually write this as B times the dot product between A and C, whereas these are all vectors, I should have made that clear, minus C dot A multiplied by B right here. And basically what that does is it takes out all of the annoying cross product terms, because doing the cross product is rather annoying, and it's much easier to do the dot product between vectors. So let's go ahead and just evaluate the expression that's inside the integral first. So we're going to get del cross J cross 1 over R squared R hat is equal to B, which is our central term. So we're going to get J, our J vector, multiplied by A dot C. So this is going to be, this is our A, this is our C right here. So we're going to get J times the divergence of 1 over R squared in the R hat direction, minus C dot A. So we're going to get 1 over R squared R hat dot producted with del, all multiplied by our J vector right here, our current density. Now, this is actually quite complicated to show, but this second term right here actually evaluates to 0 when you integrate it. So we can actually just ignore, when substituting this back into the integral, we can actually just ignore this last term completely, which is quite nice. So we actually are only interested in this first term right here. If you want proof of that, I'll provide a resource down in the description. But suffice to say that this second term is just 0 when you integrate it, so there's not really a lot of point in including it in the integral. So let's go ahead and substitute this in. So we're going to get curl B is equal to mu naught over 4 pi times the integral, and we're going to get J times the divergence of 1 over r squared in the r hat direction, integrated over the volume right there. Now this divergence of 1 over r squared is actually a bit of a tricky beast, because when you look at the divergence in spherical coordinates, you actually find that if you just have 1 over r squared, you actually find that you get this being equal to 0 for all points in space. Now, this actually isn't technically true, because whilst it is 0 at all points in space, if it's not actually a 0 at the one point in space which we're actually considering, which is of course the origin point of our coordinate system. So if we have a charge placed at our origin point right there, and we say we construct a spherical shell, which is going to be our closed surface which we're evaluating the divergence over, and of course this charge is going to emit an electric field which is in fact proportional to 1 over r squared, then if we were to just calculate the divergence of spherical coordinates, then we'd actually find that it doesn't have a divergence. And of course that's nonsense, because an electric field does pass through this surface right here. There is a net field outwards. So how do we get around this? Well, to come to our rescue, we have our old friend, the delta function, which is our kind of physicsy cheat thing, which the mathematicians don't really like. But this delta function basically describes exactly what we have. We have a charge distribution that's basically 0 at all points in space, except the origin point right here, where of course it's non-zero, and that's what's producing our electric field, our 1 over r squared relationship right there. So the divergence of 1 over r squared in the r hat direction is actually a delta function. Now, because we're in 3D, we actually put that this is a delta cubed function. So whereas in 1D it would just be delta of x, because we're in 3D spherical geometry, this is a delta cubed of r, where r is the radial component. And to normalize it, to make sure that it's kind of 1, because of course the area of any delta function must be 1, you actually multiply this by 4 pi right here. And that just basically is an angular integration constant. This is all the theta and the phi bits. So when you integrate that all out, you get a factor of 4 pi. So this is our result. And now we can just substitute this into our expression right here. And what did we say we could do with the delta function? Well, the delta function has this really nice property where you don't actually have to do any integration whatsoever, because of course this delta function just sifts out the one value in which it's non-zero, because that's how the delta function is defined. The area under a delta function across all space integrated over x is equal to 1, and the same thing happens with 3 dimensions, except that the integral over a cubic delta function is simply equal to 1 right here. So essentially we just have an integral of 1, so we can just write mu naught over 4 pi. We could bring our 4 pi out, we can see they're going to cancel, but our delta cubed dv term right here is just going to equal 1. So we just multiply by the current density right here. So 4 pi is going to cancel. And so what are we left with? We're left with curl of B is equal to mu naught times J, which is this remarkably simple result. And this is what's known as Ampere's law right here. And it basically is telling you that if you have a current and you actually have a magnetic field which arises from the current. And this is very similar to Gauss's law, where you actually have the divergence of E is equal to rho divided by epsilon 0. So whereas with electrostatics, you have this equation right here, where of course you have a charge density producing an electric field. In this case, you have a current density right here producing a magnetic field, which kind of goes back to exactly what we were saying about magnetic fields, because all they are is just charges that are moving, essentially. So if you have a moving charge, or lots of moving charges in this case, causing a current, then you have a magnetic field. And of course, the main difference is that this magnetic field is actually at right angles, hence this cross product term right here. So there is a nice kind of little symmetry, but it's not quite the same, which is really interesting. So what we can actually do is, similar to Gauss's law, we can actually transform this equation right here into integral form. And the way in which we do this is by integrating over a surface right here. And basically it's just a surface which is going to encapsulate a certain amount of current that's flowing through. So say we have some current that's flowing through here, we can construct a surface that is going to tell us how much magnetic field is produced as a result of the current that's enclosed within this surface. So let's go ahead and do our integral. So integral of the curl of B over our surface, so there's going to be a dot product ds, is equal to mu naught times the integral of the current density over the surface right there. Now, on the left-hand side, we can apply Stokes's theorem, which we derived in a previous video. And basically, Stokes's theorem says that you can actually convert this to a line integral as long as the surface is bounded by the line. So essentially, this can look something a bit like a net or a bag or something right here. You can have this surface right here, as long as this surface is kind of bound to this line right here. So we can convert this to a closed line integral of b dot dl right here, where L is our kind of vector along the line, along the perimeter or the circumference in this case. And that is equal to mu naught. And what's J ds? Well, current density, current per unit area times area is just current. So this is going to be the current right here. But it's important to note that this is the current enclosed within this surface right here, the current that's flowing through this bag, if you like. And this right here is the integral form of Ampere's law right here. The closed loop line integral of a magnetic field is equal to the current that is flowing through the surface right there. So what's nice is you can actually use this integral equation to derive what the magnetic field is for a wire that's carrying a current right here. And this is probably the most common application of Ampere's law. You can use it for a couple of other things, but this is by far the most common. And what we're going to do is we're going to consider a wire. It's going to be an infinite wire in this case. And this wire is propagating along the Z direction right here. So it has a current that is propagating along the Z direction. Now, in this problem, it's very, very handy to use cylindrical coordinates because this is a system which actually has cylindrical symmetry. And what do I mean by that? Well, it doesn't actually matter whether you're here or here because, of course, this is an infinite wire. And so it doesn't really matter how far along this Z direction. It should be the same. There's no reason for it to be any different at this point than it is at this point. And so what we say is that this is cylindrically symmetric, and so therefore it's very easy in this case to solve this problem using cylindrical coordinates. So what we're going to do is we're going to construct an Amperian surface which is going to enclose all of the current that's flowing. So we have our current flowing, and this surface is basically going to be a ring, essentially. This is an imaginary surface right here. In fact, to do that, I'll just do this in dotted line. So this is our imaginary surface. And through this surface, we have, of course, a current that's penetrating through the surface. So how do we get the magnetic field? Well, what is this closed line integral right here? How do we quantify this? Well, we can actually express an infinitesimal line element dl, we can actually parameterize this in terms of cylindrical coordinates. So what direction is this dl kind of pointing in cylindrical coordinates? Well, if this is the z direction and r is our kind of radial coordinate away, then this dl is in fact in the angular, the theta component. So we can actually say that dl is equal to dl as a scalar times the theta hat direction, because of course our unit vectors just point in a certain direction. But how do we express this dl element in terms of cylindrical coordinates? Well, we can actually write that dl is equal to r d theta right there. And the way in which you can just kind of think of this is like just considering an arc length right here. So if that's dl and this is our radius r right here, then of course the arc length is equal to the radius times the angle right here, which is in our case theta. So that's kind of how you can think of that right there. So we can write this as r d theta in the theta hat direction. So dl only has a theta component, which therefore means that B, our magnetic field, must also only have a theta component. So the way we write this is like that, in that B will only have a theta component because all other components will just kind of cancel each other out. So B dot dl right here, that's just going to equal B theta times dl, which is r d theta right here, because of course theta hat dot theta hat simply equal to 1. So therefore the integral all the way around our closed curve right here is equal to b theta r d theta. And what are the limits? Well, theta as an angle spans between 0 and 2 pi. That's the entire domain of theta, or 360 degrees. And this is equal to mu 0 times I enclosed right here. Now, in this example, the only enclosed current is just, well, the current of the wire. There's no additional current, but it's important to note that this will not always necessarily be the case. And in the next examples we'll get on to, we actually need to be a bit careful about what current we're considering. But for now, we can just write that this is equal to mu 0 I. So integrating this out, we're going to get b theta times r times the integral of d theta over 2 pi, which is just, well, 2 pi, is equal to mu 0 I right here. And rearranging this for b theta, we just get that it is equal to mu 0 I divided by 2 pi r. And one final thing is just to express this as a vector. So the b vector is equal to mu 0 I divided by 2 pi r in the theta hat direction. So we have the result for our magnetic field around a wire as a function of the radial distance away from the wire. Now, this equation is telling us that the magnetic field is in the theta hat direction, so it's kind of circulating around. So if you were to draw the magnetic field lines, you'd find that they are essentially going around and round like that. So they're closed loops in this case. And our current, of course, we said was propagating along this direction right here. This intensity of the magnetic field decreases as a 1 over r dependence. So that's the result for a very small wire right here. But what about if we have a thick wire? And what do I mean by that? Well, I mean that we are actually within the wire itself. So at the moment, I'm just drawing a wire. I'm not drawing any Amperian surface. And we have a really, really thick piece of wire right here. Let's just pretend. And within this wire, again, we have a current right here. Our current is flowing again in the z direction. And this current is equal to I, like we had before. Our total current of this really thick piece of wire is just equal to I. And we're going to assume that this current has a constant current density J right here. So in this case, I is equal to J times the surface area, which is of course pi r squared, where r is the distance right here. Okay, so far so good. So what happens when we try and evaluate the magnetic field inside the wire? So of course we know what it is outside, we just derived it, but what happens when we're inside the wire? Well, again, we can construct our Amperian loop, but this time because we're inside the wire, we're going to construct it within the loop. So this is going to look something a bit like this. And so here is our loop, and it's encapsulating a certain amount of current right here. And just like before, it's facing the same way as the current, and so therefore the line outside will also be in the theta direction. So let's go ahead and write out our integral. So we're going to get the closed loop integral of b dot dl is equal to mu naught times I enclosed. And this is why we need to be a little bit more careful about what current we are considering, because the enclosed current in this surface right here is not the total current right here. We actually need to transform this into what the enclosed current is going to be. So, of course, since the current is proportional to the area, hence this equation right here is proportional to pi r squared, then the enclosed current divided by the total current is just going to be the ratio of the two areas. And so the enclosed current is going to be pi r squared, where little r, where our sort of evaluation r right here, divided by the radius of the actual wire, capital R right here. And so the pi's are just going to cancel. So we can then write that the enclosed current is equal to the total current times r squared divided by r squared right here, because of course J is the constant, and that's what's led to this equation right here. So let's go ahead and substitute that in. So what's going to happen? Well, this integral, because we're doing essentially the exact same integral over our kind of loop, our closed loop, this is just going to equal b theta times 2 pi r yet again. So this hand side of the equation will stay the same. But now, of course, we have a different thing on the right. We're going to have this mu naught IR squared divided by capital R squared. So this time, this R is going to cancel with one of the R's on this side, right there. And we can arrange to get b theta is equal to mu naught I R divided by 2 pi times capital R squared. Should have been a squared right there. And then just to write this as a vector, we get b as a vector is equal to mu naught I R divided by 2 pi r squared in the theta hat direction, as we had before. And so this is quite an interesting result. This is actually telling us that inside the wire, then it's telling us that at greater distances away from the kind of central axis, the z-axis, then the magnetic field actually increases. And so if we were to actually just graph the magnetic field looks like for a wire that's thick, so our wire is of radius capital R right here, and then we're plotting B of lowercase r, where lowercase r is just the point where we're trying to evaluate the magnetic field, the radial coordinate. Then we actually find that it's linear, because of course B is simply proportional to R. It's linear right here, which is a straight line. But of course we said that once we get to this point right here, we actually got this 1 over R dependence that we had before, right there. And so it's going to fall off something a bit like that right there. So you have this interesting kind of discontinuity happening at the boundary right there. And so this is kind of what's going on for a magnetic field that is inside a wire, both inside a wire and outside a wire. And that's kind of the main application of Ampere's law. So just again to reiterate, this is proportional to R, and this is proportional to 1 over R, this part of the graph. And this kind of change happens at when R is equal to R. Now we're going to consider one other common example of Ampere's law being used. And in this case, rather than considering just a wire, we're actually going to consider a solenoid. And this is basically just a coil of wire right here. So you may be familiar with it. It's just essentially a coil, a spring of wire right there. And we're going to pass a current through our coil of wire, just like we did before. So we're going to have current I, and it's going to sort of go in this direction, and it's going to maybe go out this direction. But the key thing is that the current has to go through a coil of wire. Now, just like with the previous problem, this problem yet again involves cylindrical symmetry. I mean, the coil is essentially a cylinder almost, really, isn't it? But what's going to happen to our magnetic field when we have this kind of scenario right here? Well, in this case, we're going to construct a slightly different shaped Amperian loop. And we're not only going to do that, but we're actually going to construct two Amperian loops. And the first one is going to be completely outside of this coil right here. So this Amperian loop is essentially just somewhere completely separated. And we're going to call this separation distance, and remember this is of course the z-axis, and this is going to be our radial axis. This is going to be A right here. We're going to call this distance A. And we're going to call this distance right here as being equal to B. So B is going to be the slightly longer distance right here. So let's go ahead and do what we do normally. Let's go ahead and evaluate the magnetic field using Ampere's law. So B dot dl. Well, what's dl in this case? Well, we know that for symmetry reasons, we're not actually going to get a magnetic field along this side or this side. There won't be any kind of radial component this time. And if we think about kind of why that is, well, if we imagine just a really small little magnetic field produced around this current, it's going to look something a little bit like this. So this is going to be, because of course we said the magnetic field produced around a current is just going to be like a ring. Well, if you do that for every single one of these things, of these loops right here, you actually find that you don't get any net radial component that's coming out. So the radial component of B is simply equal to 0, which means that these two sides, which of course signify the radial component, are equal to 0 right here. So we're only going to get this side and this side actually contributing to anything. So what are we going to get? Well, if we're going around in this direction, then we're going to get that this is going to be the magnetic field times our length, which let's just call L of our Amperian loop. So this is going to be the magnetic field evaluated at point A right here times the length. But since we're going around a loop, then this is actually going to be subtracted from this side right here. So this is going to be minus the magnetic field evaluated at radial coordinate B, again, times the length right here. And this is equal to mu naught times I enclosed right there. But of course, we've just constructed an Amperian loop in the middle of nowhere. There's no current at all out here. So this is just going to all equal 0 because there's just no enclosed current right here. Then B must be 0 everywhere outside the solenoid. So, well, that's not very helpful because otherwise what's the point of a solenoid? We know that a solenoid produces some kind of magnetic field. So let's go ahead and redraw our solenoid, but this time we are going to put our Amperian loop, we're going to sort of stick it half in and half out of the solenoid right here. So we have our loop. Again, this side is oriented along the Z direction and this side is oriented along the R direction, the radial direction. But this time we're kind of half in, half out. And of course, it's still of length L right here. So let's go ahead and do exactly what we did before and evaluate the magnetic field, the total magnetic field along this kind of closed line integral. So the integral of B dot dl is equal to mu naught I, which is Ampere's law. And remember, it's the enclosed current right here. And because for symmetry reasons, we again know that this side and this side are just going to be 0. So they are not going to contribute anything whatsoever. But what about this side right here? Well, like we said with the boundary conditions, we know that the magnetic field has to be zero anywhere outside of the solenoid. Because of course we have to have a smooth function outside the solenoid. We can't have any sudden discontinuities outside the solenoid, and so therefore BL along this kind of side right here is just going to be equal to 0. So we're going to get nothing from that side of the Amperian loop either. So the only side in which we're going to get a contribution that's non-zero is the side that's inside the solenoid right there. And so what's this going to be? Well, that's just going to be B times L right here. So that's going to be plus BL because, of course, this is our Z direction and we're integrating along dl is equal to dz in this case. And that is equal to mu naught times the enclosed current right there. So, but what is this enclosed current? Well, you'd think it might just be the current that's flowing through. But actually, within this kind of distance L, we actually have the current being repeated several times. In this case, we've got 1, 2, 3, 4, 5 kind of repeats. So instead of just getting the enclosed current, we actually have to multiply this by the number of turns that this length has kind of encapsulated right here, which we're just going to call n for now. So this is just simply the number of turns that spans this length L, multiplied by just the current that's flowing in the wire that we kind of know about. And so rearranging this, we're going to get that B is equal to mu naught Ni divided by L. And of course, since the only side of this Amperian loop that contributed something that wasn't zero was oriented along the Z direction right here, then that means the magnetic field is in the Z direction. So therefore B as a vector is equal to mu naught Ni divided by L in the Z hat direction. However, it's more common to just express this N over L as the number of turns per unit length, which we'll just use lowercase n for. And this is just the number of turns per meter, essentially. And so that's kind of a better way of writing it, just because you then don't have to count each individual turn. So we're just going to get mu naught times n times I right there. And this is our final result. So this is the magnetic field that is produced inside a solenoid. So let's go ahead and go back to what we were considering before. We have our coil of wire right here. And we said that outside of the coil of wire, because it has to satisfy the condition that B equals 0 at infinity, we know that the magnetic field is 0 everywhere outside of the wire. But inside the wire, we have this result that B is equal to mu naught I times the number of turns per unit length right here. And of course, it's just in the Z hat direction. So we're going to simply get a magnetic field that looks a little bit like this. And so we get a magnetic field that's more or less straight within the solenoid. But of course, once we go outside the solenoid, it will start kind of bending off to various different directions. If the solenoid is infinitely long, which obviously again isn't possible, but if we idealize it for a second, we say this solenoid is infinitely long, then B will only have a Z component right here. And we're only considering what's the case inside the solenoid. So there we go. I hope that was really, really helpful. So Ampere's law actually isn't the final version of Maxwell's law. There is actually one thing that's missing from this equation that we've actually been using so far. And this is something we'll be discussing further along in the series. But in the next video, we're actually going to be using this coil of wire and kind of reversing the situation. So rather than passing a current through the coil of wire, we're actually going to have our coil of wire, but instead pass a magnet through the coil of wire. And we're going to see what happens when we do that. So I hope that was really helpful, guys, and I'll see you in that video. Take care.